There is danger in the line of fire. Caution. Confined fluid power. Let's take a look at a pneumatic system where it is clear that we do not want to be in the line of fire. Here is a gun barrel into which we will place a cartridge. When we fire the cartridge, hot gases are generated, building up pressure behind the bullet. When the pressure is adequate to overcome the resistance of the bullet begins to move down the barrel, increasing velocity as the ever-expanding hot gases continue to accelerate the bullet during its travel down the length of the barrel. You do not want to be standing in the line of fire of this fluid power system. It was this characteristic of pneumatics that claimed the life of an experienced maintenance man at a lumber mill while he was attempting to repair a hydraulic accumulator. He, along with some others, were working on a piston-type accumulator where the hydraulic fluid had been properly drained. However, the end cap on the nitrogen end was very tight, and they were not able to unscrew the cap using a standard wrench. A cheater bar was brought in to help overcome the torque so they could open the cylinder and make the necessary repairs. Let's take a look at a piston accumulator and see exactly what it looks like. A piston-type accumulator is made up of a cylinder with threaded ends, a piston, and end caps. The cylinder is filled with high-pressure nitrogen and then plugged. The opposite end is exposed to the high-pressure hydraulic fluid, and the piston is moved until the nitrogen pressure and the hydraulic pressure are equal. The piston separates the gas from the hydraulic fluid. When servicing the accumulator, it is important to drain the pressurized hydraulic fluid from the accumulator. However, a common and very dangerous mistake is to think that once the hydraulic pressure is relieved, there is no more trapped pressure. As you can see, there is still full nitrogen pressure on the right side of the cylinder. If an attempt is made to remove the end cap from a gas pressurized accumulator, the cap may unthread until the remaining threads can no longer withstand the force exerted by the gas, and the cap will be ejected away from the cylinder with a very high rate of acceleration. At the same time, Newtonian law is in effect, and the accumulator body reacts with equal force in the opposite direction. Anyone standing in the way of either of these projectiles would be in the line of fire. Let's take a look at what is really going on here. After I had created that first slide, I got thinking about the math that was actually behind all this, and I thought it would be good to add some numbers here so we can actually see the forces and the speeds that are involved. Given a 150 millimeter bore with a pre-charge of 104 bar, what would be the force pressing on the end cap of the accumulator? Now I know a bunch of you are reaching for your calculators because you can't wait to figure this out, but in the interest of time, I'm going to give you the answer to this question. The amount of force would be 183.783 kilonewtons. Well, for those of us who remain metrically challenged, that would be a 6-inch bore with a 1,460 psi precharge, giving a force of 41,314 pounds. The end cap weighs 45 newtons, about 10 1/8 pounds, and Isaac Newton informs us that acceleration equals force divided by mass. That tells us that the acceleration is 131,362, which is about 4,080 times the acceleration of gravity. In 7 milliseconds, the cap would reach a velocity of about 280 meters per second and would have covered a distance of 1 meter. In addition, the expanding gas would have an endothermic reaction, instantly freezing any skin that it contacted. The experienced maintenance man was instantly killed when he was struck by the cap as it broke loose, and 2 others were injured by flying parts of the accumulator. This accident may have been avoided if the maintenance people had recognized the warning of the cap being hard to remove and then making sure the nitrogen pressure had been relieved. In fairness, the fact is there was a pressure gauge on the nitrogen end which was not giving a correct reading. They thought that there was no gas there, and they went ahead anyway. The danger of compressed gas in fluid power systems is usually from projectiles that are caught in the stream of exhausting gas and not from injection of the fluid itself. With higher pressures, there is also the danger of local freezing of exposed skin due to the endothermic reaction of the expanding gas. Looking at the hydraulic end of the accumulator, we find some different dangers when being in the line of fire. There is the danger of a fluid injection injury from the uncontrolled release of stored energy, and there is also the danger of being hurt when a mechanical part moves due to the unexpected release of stored energy. The next several slides will show a common circuit with a bladder accumulator. We will examine the 5 locations where someone could be placed in the line of fire. We will also see how to prevent an accident from occurring. A bladder-type accumulator is made up of a steel or composite bottle with a bladder that separates the gas from the liquid. The bladder is filled with gas, usually nitrogen, and then plugged. A pump directs flow into the accumulator, compressing the gas in the bladder until a set pressure is reached. When the directional valve is shifted, high pressure from the accumulator is directed to the cylinder, lifting the load. The directional valve is returned to the center position, and the load remains raised. So what are the potential hazard areas? Well, there is energy stored in the cylinder holding the load, and there is also energy stored in the accumulator. If our super mechanic opens the line to the cylinder, he will be in the line of fire. Even if he remembers to drain the line to the cylinder, he can still be in the line of fire if the directional valve is shifted. If the directional valve is shifted, he will also be in danger of an injury from an unexpected mechanical movement. If he opens a line between the accumulator and the directional valve, he will be in the line of fire. If he drains the accumulator, he will still be in the line of fire if the directional valve is shifted. The only way for our guy to avoid being in the line of fire is to be sure the pump has been turned off, the energy has been released from under the load, and the energy has been released from the accumulator. As you can see now, there is no more stored energy, and our guy will be safe to work on any part of the system without being in the line of fire. A fluid injection injury is a pressure-caused insertion of fluid, such as paint, hydraulic fluid, etc., into the body. These injuries generally occur when servicing paint guns, hydraulic leaks, diesel injectors, and grease guns. Fluid injection injuries are relatively rare, and as a result, many of our emergency responders are unfamiliar with the severity and proper procedures for managing these injuries. When there is a high-pressure injection of the liquid, there is usually only a minor sensation of discomfort on the part of the injured person. What is actually happening out of sight is something called compartmental syndrome. The injected material, even if it is water, fills the channels, compartments, surrounding the nerves, tendons, and muscles, pinching off the supply of blood. The tissue immediately begins to weaken and will eventually die if not treated quickly and properly. Now, some statistics about the severity of these injuries. Overall, the statistical chance of an amputation after a high-pressure injection injury is 48%. You remember that from a couple of slides ago. If the liquid includes solvents, this rate increases up to 80%. If the pressure is above 7,000 psi, the rate approaches 100%. There are some typical permanent complaints from those who have had high-pressure injection injury, including permanent pain, sensitivity to cold, lack of normal feeling, and that's not about your emotions, and reduced range of movement. Only a small percentage recover enough to return to their original job responsibilities. This is a very serious type of injury. Another statistic that is revealing is that the average time between the actual high-pressure injection and the time the injured person seeks medical help is 9 hours. The reason for the delay is that the injury may appear small and benign, and the injured person feels foolish complaining about it. The chance of having an amputation approaches 100% if medical attention is not given within 10 hours from the time of injury. Now, just look at these numbers again. The average time between an injury and when someone goes for help is 9 hours. After 10 hours, the chance of an amputation is 100%. Now, if the average time is 9 hours, that means a lot more of them are going over the 9 hours, which means there's a lot of amputations. It's very, very important that we who have responsibility for our people recognize this, so that if one of our people gets an injection injury, we don't say, tough it out, go back to work, it's no big deal. It calls for immediate attention and immediate medical response. In the world of fluid power, our conductors and connectors, that is hoses, tubing, and fittings, are a source of potential high-pressure injection injuries. Pinhole leaks, burst hoses, and incorrect assembly or disassembly account for many accidents and near accidents. We will take a look at the basic structure of a hydraulic hose to help us understand the how and why of leaks and bursts, and also how we can prevent and protect against an accident or injury. Hoses are constructed of three main components: the tube, the reinforcement, and the cover. And I hope that you have a slide presentation that's large enough to be able to see these, but this is the basic structure of any hose. The inner tube is a very flexible part that is the actual conveyor of the fluid, and then there is the reinforcement, which is what is able to withstand the pressure, and then the outer cover is that which protects the reinforcement in the inner tube from wear and from abrasion and that type of thing. The inner lining or tube is used to conduct and convey the hydraulic fluid and must be resistant to the fluid being conveyed. Hose manufacturers' catalogs, in their engineering and technical section, have several pages of tables devoted to chemical resistance. These tables have compatibility rating scales for the various chemicals as they apply to the manufacturer's particular hose and fitting materials. The charts can be quite extensive, but are vital to safe and practical hose applications. Hose selection must assure compatibility of the tube, cover, fittings, and O-rings with the fluid being used. And by the way, this text was taken right out of the Connector and Conductor Study Guide, from the International Fluid Power Society. Protective covers for hydraulic hose assemblies are taking on a whole new meaning. They are still being used to protect hoses on mobile construction and mining equipment. However, with the need for higher pressure systems and more compact machine designs, design engineers are increasingly looking for ways to safely protect machine operators and personnel from catastrophic hydraulic. First and foremost, the best way to protect a hose assembly, especially from abrasive wear, is to reroute it away from hose to hose and hose to metal conditions. A second option is to specify a hose made of special hybrid compounds. Some of the new hybrid cover materials have been tested to last up to 300 times longer than standard rubber-covered hoses. To further protect hydraulic hoses from external damage and wear, design engineers can use several different types of hose guards or sleeves. And while these sleeve covers may protect a hydraulic hose from abrasion and cuts, they typically offer little or no protection from the hose bursts and pinhole leaks. Excessive pressure surges, flexing, kinking, crushing, or exceeding the minimum bend radius may cause a burst away from the hose ends. Pressure surges that exceed the hose's maximum operating pressure rating may result in reinforcement failure. Excessive flexing, kinking, and crushing can cause reinforcement fatigue and eventual failure. Bending the hose tighter than recommended will place excessive stress on the reinforcement, which opens large gaps between strands of reinforcement and will severely reduce the hose's ability to withstand pressure. I will try to explain that a little bit better in the next slide. A pinhole leak in a hydraulic hose that is under pressure can release toxic fluid at more than 600 feet per second, close to the muzzle velocity of it. Although it is the hose's high-tensile wire reinforcement structure that bears the brunt of the pressure, the inner tube itself has to bridge the gaps in the braid formed when the hose is bent and stressed. If the compound of the inner tube is not strong enough, it will be blown through the gaps in the braid, which can cause a scissoring effect and cut a hole in the tube, resulting in a pinhole leak. The very fine jet of hydraulic fluid at high pressure will act like a hypodermic needle that may penetrate both protective clothing and skin. To protect operators of hydraulic equipment from catastrophic hydraulic hose bursts or pinhole leaks, several hose manufacturers have developed their own versions of a safe, line-of-sight nylon sleeving. The inside sleeve layer is made of extruded nylon fiber that elongates or stretches up to 20%. By stretching, it can absorb the energy of a burst or a pinhole leak, and the outer sleeve contains the fluid and redirects it to the clipped ends. A burst or pinhole leak in a hydraulic system can cause serious problems, including personal injury, fluid burns and injection, fires and explosions, electrical shock, and mechanical failure, especially for anything or anyone located within a 3-foot line of sight. So, how can we protect our people? We have talked about the danger. We have talked about engineered solutions such as hose guards. We are trying to educate by increasing awareness by means of this seminar and the introduction of the safety card. There is one more area of education that we need to consider: certification. One major hydraulic hose and fitting manufacturer has stated that on any given day, somewhere on the planet, they have a lawyer in court because of a component failure. In almost every instance, the problem was the improper application or assembly of the hose. It was this kind of information that led the major connector and conductor manufacturers to approach the IFPS to produce a certification for covering the application and assembly of these components. This is now the certification for connector and conductor, our CFP-CC. Training for this certification is rigorous, but those who attain it will gain a level of competency and proficiency that will serve to protect them and those around them finding themselves in the line of fire. Okay, there's a warning. The following slides do show graphic pictures of actual injection injuries and what was required to properly treat them. Not for the squeamish, but necessary to understand the seriousness of the problem and the need for proper treatment. This injury appeared to be just a small puncture wound at the base of the index finger. The injured person went back to work and did not seek help until after his shift. By that time, the hand was throbbing and he had lost mobility and his fingers were getting numb. X-rays revealed the damage being done and the location of the injected fluid. The compartment syndrome had set in and he was in danger of amputation. The surgeon located the areas that would need to be excised, and then the work began. The various compartments had to be opened and drained, and the dead tissue removed. In this next instance, a paint spray gun had injected fluid into the left hand of an operator, but he waited 12 hours to seek help. And if you recall, the average time is 9 hours, and after 10 hours, the chance of amputation is 100%. An effort was made to drain the wound area, but you can see the black middle finger. The effort continued, but after 48 hours it became a matter of how much of the hand could be saved. What started out as a treatable injection injury ended up costing 2 fingers and an almost complete loss of function in the hand after all the dead necrotic tissue was removed. So, what do we do? Well, we must train our people about the dangers of high-pressure fluids, including compressed air, nitrogen, hydraulic fluid, grease, etc. Always be sure pressure is relieved in the system before doing any service or repairs. Never search for leaks by placing a hand near the suspected area, even while wearing gloves. Be sure people are properly trained to assemble connectors and conductors to prevent leaks. We must train our emergency responders on the proper method of handling a high-pressure injection. This slide is of a protocol that has been established here at McMinnville with the local emergency room and with our EMTs on just what to do in case of a fluid injection injury. This is not original with me. It is something that I got from a website, which you can see at the bottom, from a hospital in Australia that had put together this program. I found it to be very good and effective. I went over to our own emergency room and asked what their protocol was, and they really didn't have any. And so we sent this to them, and we also spent the time with our emergency responders so that they would know what to do and also would be careful to take a fluid injection injury very, very seriously. So here is the step-by-step procedure, beginning in the green area of what to be done at the site of the injury. And as you can see, it's necessary to keep the person warm, identify the fluid, and then immediately transport them to the hospital. Again, one of the big dangers of the fluid power injury, especially if it's an injection injury, is to not take it seriously. And whether it be the person injured or those of us who are supervisors, we need to recognize that so the person does not just go back to work and ignore the injury. When we see such an injury, no matter how benign it may appear, they need to be immediately brought to the medical facility where they can be evaluated as to whether or not there has to be surgery involved. Now again, it's important that the emergency room also have that information, because if they don't have the information, as mentioned earlier, sometimes the doctor will send them home with some painkiller, not recognizing the danger that is there. That is not the doctor's fault. This is a very rare injury, and it's very important that they understand they have that information. The International Fluid Power Society has crafted a safety card, which is being sent to every member of the society, and the card will also be available for purchase for non-members for a nominal fee. The card is wallet size and provides important information as to what to do in the event of an injection injury. Because immediate local, and appropriate treatment is necessary. There is a space on the card for the individual to place the contact information of the best local medical facility that has the knowledge to properly treat the injury. The fact that members, employees, and employers will have the card will not only increase the opportunity for proper treatment, but will also increase the awareness of the danger. Here's a copy of the safety card, both the front and the back. And as you can see on the back, there are a number of questions that are asked, which is the information that the medical facility would need to have in order to properly treat. And as you can see in the face of the card, there is a place for you to put the information of the medical location that has the best opportunity to properly treat this injury. It is important that our people be protected from a fluid power injury. We cannot protect them with a suit of armor. We can make engineered solutions, such as limiting access to within 1 meter of pressure lines, routing hoses so they do not chafe, providing line-of-sight sleeving. We can provide educational solutions such as training on the potential dangers, proper lockout-tagout procedures, certification so only qualified people actually assemble hose, tubes, and fittings. That concludes In the Line of Fire. I do thank you for your time and your attention, and if you have any questions, you can write to me or you can respond and let us know what you think. Appreciate your time. Thank you very, very much.